Hi, and welcome to the next section in our Understanding Orbits lesson. In our last section, we covered some basic but important information about orbits and trajectories of a space mission. We now understand, through the example of throwing a baseball, that the force of gravity allows us to predict, explain, and identify the motion of nearly all objects in space. Now, we're going to move on to the basic fundamental laws of motion that Sir Isaac Newton developed. In this section, we'll discuss Newton's 3 laws of motion, how we define weight, mass, and inertia, how momentum and changing momentum relate to spacecraft, what Newton's law tells us about action and reaction, and finally, where gravity fits into this big picture. It's amazing but true that no single person thus far has had a greater effect on science than Sir Isaac Newton. All of his discoveries could fill volumes, and you'll learn more about them later. But for now, we're going to focus on Newton's laws of motion. First, you have to accept the given that Newton's laws of motion are unbreakable. That means there are no exceptions to these laws. They apply to everything in our known universe. This is great because we have something we can really count on. Newton's laws of motion can explain the motion of the heavens, the paths of the stars, and the future position of Earth. Here you can see the man himself. This next slide may make you hungry for more information about space. Actually, we'll use this burger to illustrate a new way of looking at weight. When we put a quarter pounder with cheese on a scale, guess what? It has a weight of about 1/4 pound, but it only has a mass of about 1/10 of a kilogram. What exactly is mass? Well, if you said that mass is how much matter or stuff is in the hamburger, you'd be correct. Knowing the mass of our hamburger, we automatically know 3 useful things about it, which we'll discuss next. If you weigh yourself occasionally, you probably use a weight scale of some kind. This scale measures how much Earth's gravity is pulling on your mass. In the US, we often refer to our weight. In Europe and many other countries, people worry about their mass, not necessarily their weight. Before we talk about mass, let me introduce you to the character shown on the slide. This person is actually a caricature of the primary author of your text, Jerry. Let's let Jerry help us understand Newton's laws. We just learned that mass was how much matter or stuff an object has. You can see in this first illustration that Jerry is measuring the mass in the cube. The general rule here is that more stuff means more mass. Knowing the mass of an object also tells us how much inertia it has. Another way of saying this is that inertia of an object tells us how much the object resists motion. If you have a big brother, you probably notice that if he's sitting in front of the TV, he doesn't move much. He resists motion. You can see in the second illustration that Jerry is testing the cube's tendency to stay at rest unless acted on by an outside influence. In the third illustration, we note that the green object has mass, and that mass is exerting gravity on Jerry and attracting him to the green object. And believe it or not, the green mass is actually attracted to Jerry. Any 2 masses will exert gravity on each other depending on their masses and the square of the distance between them. You may say that the green object and Jerry make an attractive couple, but then again, you may not say that. For us, the Earth is a gigantic mass that exerts its gravity on us. Remember, anything having mass will exert gravity on other masses. Okay, now that we have a working knowledge of mass, weight, and inertia, we're ready to look at Newton's first law of motion. For each of these laws, consider the words carefully and think about some examples that demonstrate the laws. Newton's first law of motion states that a body continues in its state of rest or of uniform motion in a straight line unless compelled to change that state by outside forces. Objects at rest stay at rest. Think about a couch potato resting in front of the television. He will stay at rest until someone forces him to move. Newton's first law of motion also applies to you riding a bicycle. Imagine you've worked to get your bicycle going at a constant speed on a flat road. Now, if we ignore friction of the tires on the road and the drag of the wind, when you stop pedaling, the bicycle would coast forever. you'd have to apply a force like the brakes to slow it down. So, how do we relate Newton's first law to a spacecraft? You're right. A spacecraft in motion falling around Earth tends to stay in motion unless acted upon by an outside force. What causes a spacecraft to fall around Earth? Gravity is the correct answer. Okay, let's expand this concept. You're sitting in your chairs now and are at rest. Your body resists movement based on its mass or how much stuff you have, which includes any change in your pockets, your car keys, and even belly button lint. So, your mass determines how much inertia you have, which indicates how much you resist motion. Let's say you're driving in your car to the grocery store. You and the car have a certain mass and you're traveling at a certain speed. The combination, or product, of your mass and speed is called momentum. You can also think of momentum as resistance to a change in speed or direction. So, you and your car have a certain momentum. If you want to stop, you must apply a force, the brakes, to slow your speed. Or if you want to change the direction you're going, you have to crank the steering wheel, applying a force to turn the car. So, if a mass is traveling at some speed, it has momentum equal to the product of its mass and speed. The more momentum an object has, the more it will resist a change in its direction or speed. We'll go over some more examples shortly. Now that we understand the basic idea behind momentum, let's talk about two types of momentum: linear momentum and angular momentum. An object's linear momentum is its resistance to changes in its straight line motion. The object's resistance to change depends on both its mass and its velocity or speed, as we talked about on the last slide. Now, I'm going to throw you a curve here. If we have a spacecraft in orbit falling around the Earth, it's not moving in a straight line. The spacecraft has mass and velocity, but the motion is not in a straight line. What's going on? You're right. There's a force acting on the spacecraft, changing its direction. What's the force? Right again, gravity. So, a spacecraft of a certain mass going a certain velocity will have momentum. But the force of gravity keeps changing the direction the spacecraft is going, keeping the spacecraft in orbit. Now, you understand the gravity of the situation. All right, why don't we try another example? In this figure, you can see two aircraft. The one on the left could be a fuel tanker that is about to provide fuel to the jumbo C5 aircraft on the right that is pulling in slightly behind and lower than the tanker. Once the tanker and C5 are in the proper position with the same speed, they can begin fueling operations by extending a flexible pipe from the tanker to the C5 aircraft. Let's assume you are the tanker pilot and you are refueling a jumbo C5 transport and a smaller, lighter F-15 fighter aircraft during an aerial refueling. In which refueling operation, the C5 or F-15, would you expect to make more speed adjustments? If you realize that the fully loaded C5 has about 20 times the mass of the F-15, will that help you answer the question? During refueling, the tanker and C5 or F-15 must be going the same speed. Since the mass of the C5 is 20 times greater than the F-15's mass, the C5 aircraft would have 20 times the linear momentum of the F-15. So you, as the tanker pilot, would estimate that there would be fewer speed changes with the C5. You might try another example like this one to make sure you understand the concept. Linear motion is pretty basic because it involves motion in a straight line. We're used to this motion because we've already discussed race cars on a track and baseballs. Now we're going to move ahead to angular motion. Angular motion is a little more challenging because it deals with things that spin. So let's get down to basics. Objects at rest resist spinning. For this example, let's talk about a toy top. A non-spinning top, like the one on the left, will fall over if you try to stand it upright. In our discussion on linear motion, for an object at rest, the resistance to movements was called inertia. Well, in angular motion, for an object at rest, like our top, the resistance to spinning is called moment of inertia. The moment of inertia of an object can be thought of as its mass times its size. So, if an object has lots of mass and is big, it will have a big moment of inertia. Now, if we spin the top at a fairly high speed, what happens? Right, it tries to remain upright, and as long as it's spinning fast enough, it will remain upright. Now, the magic begins. In linear motion, the resistance of an object to change in speed or direction was called momentum. Well, with a spinning object, we call this resistance to change angular momentum. We can find the angular momentum of an object by multiplying its spin speed, or angular velocity, times its moment of inertia. So now we know that angular momentum can be thought of as an object's mass times its size times its spin speed. If you want to increase angular momentum, you can increase size, mass, or spin speed. So, to summarize, an object's angular momentum depends on how spread out the mass is from the center of spinning, which is the moment of inertia, and how fast it's spinning. Later in this course, you'll see that spacecraft often use angular momentum to keep themselves pointed in the right direction in space. Angular momentum has a direction. To find the direction of angular momentum, we just need to focus on the direction of spin and use the right-hand rule. For our spinning top, if you curl the fingers of your right hand in the direction the top is spinning, your thumb will point in the direction the angular momentum is pointing. You can use the right-hand rule on any spinning object to find the direction of angular momentum. A quarterback and a football are a great example. The quarterback puts a spin on the football, causing it to spiral as it flies to the receiver. This spin helps stabilize the football so it does not tumble in flight. So if you curl the fingers of your right hand in the direction that the football is spinning, you know the direction of angular momentum. Now let's try one more example before we move on. Barrels of rifles and handguns have rifling or ribbing spiraling down the barrel to spin a bullet and keep it from tumbling as it flies to its target. Now we'll go back to the right-hand rule to make sure we understand the concept. Look at the diagram and use your right hand again to find the direction of the angular velocity and angular momentum. Curl the fingers of your right hand in the direction of spin and your thumb points in the direction of the angular velocity or speed and the angular momentum. You've got it. So far, we've talked about objects that have linear or angular momentum. Next, we need to discuss how to change the momentum of an object. We've arrived at Newton's second law of motion. Let's define it first, and then we can discuss what it means. The second law of motion states that the time rate of change of an object's momentum equals the applied force. Remember when we discussed linear motion, we said a spacecraft would move in a straight line unless it was acted upon by an outside force. We said that a spacecraft actually falls around the Earth, and its motion is definitely not in a straight line. What force causes a spacecraft to deviate from straight line motion? If you're thinking gravity, you're right. Changing an object's momentum requires a force. It makes sense then that the size of the force is determined by how quickly the momentum is changed. And when mass is constant, the force equals mass times acceleration. An easy example is when a pitcher throws a fastball and we hit the ball with the bat. After the ball is thrown, it has a certain, mostly linear momentum. When the bat hits the ball, applying a force, the ball almost instantly changes speed and direction. Its momentum has changed. But if we're in no hurry to change the momentum, we can apply a much lower force over much more time. Now let's try another example. Let's say a bulldozer and a baby carriage are traveling at the same speed. We recall that linear momentum is mass times velocity. The bulldozer has much higher momentum because it has much more mass traveling at the same velocity as the baby carriage. In order to stop both objects in the same amount of time, we have to apply a much higher force to the bulldozer. Now, I think you're ready for Newton's third law of motion. Newton's third law of motion describes a very important relationship between action and reaction. Let's look at this picture of the two ice skaters. Look at the boy and girl standing together on the left side. Each of them has mass, but neither of them is moving, so there is zero momentum. When they apply a force by pushing away from each other, what happens? Ideally, they begin moving, they have an equal but opposite velocity, and the girl's momentum is equal and opposite of the boy's momentum. This is a great example of Newton's third law of motion. When body A exerts force on body B will exert an equal but opposite force on body A. If the skaters start at rest and the first one pushes against the second, they'll both go backward. The first skater applied an action, which was pushing, and received an equal but opposite reaction. Now, think about this fact and imagine an astronaut in the free-fall environment of space. If an astronaut tries to use a power wrench to turn a simple bolt without the force of gravity to anchor her in place, she'll start spinning instead of the bolt. Now you understand why crewed space vehicles have so many handles, braces, and straps. Newton defined his 3 laws of gravity, but when he was developing them by observing and reading about falling objects, he made a mathematical breakthrough. Pay close attention to this. Follow along with the diagram on this slide, and you'll be able to understand Newton's law of universal gravitation. We call this law universal because we believe the same principle must apply everywhere in the universe. And, in fact, everything we know about the structure of the universe depends on applying this simple law. The force of gravity between 2 bodies is directly proportional to the product of their 2 masses and inversely proportional to the square of the distance between them. If we double the distance between the 2 masses in the upper part of the figure to the lower figure, the gravity force, which we label F sub g, is decreased by 4, shown here as F sub g divided by 4. All right, let's try that again by saying it another way. Again, follow the diagram. The force of gravity decreases with the square of the distance. For example, if you double the distance between 2 bodies, the force of gravity goes down by a factor of 4. Now, take out a sheet of paper and write the equation while you think about what it means. Writing it out will help you understand this equation. Let's try an example now. Imagine you and a friend were standing 10 meters apart, and each of you has a mass of 50 kilograms. Newton's law of universal gravitation will help you figure out how much attraction due to gravity there is between you and your friend. In this case, the force of gravity between you and your friend depends on the product of your 2 masses, which is 50 kilograms times 50 kilograms, divided by the square of the distance between you and your friend, or 10 meters times 10 meters. We need to do more math to get an exact answer, but you get the idea. But if you and your friend increase the distance between you by a factor of 2 to 20 meters, you would decrease the attraction between you and your friend by 4. All right, let's recap. Acceleration due to gravity on an object near Earth depends on Earth's mass times the mass of the object times the universal gravitational constant divided by the square of the distance between the object and Earth. So, what is gravity? You don't need to understand it perfectly, but realize that it is everywhere and all-powerful. Let's look at Earth and one of its orbiting satellites, the Moon. What is the force of gravity between Earth and the Moon? Well, to put things into perspective, the space shuttle has about 7 million pounds of thrust at liftoff. The Earth-Moon gravity force is more than 1 trillion times as great as the shuttle thrust. It's important to remember that as objects get farther and farther apart, the acceleration due to gravity decreases as the square of the distance between them. So, as a spacecraft gets farther away from the center of the Earth, the acceleration due to gravity decreases. Now, you might remember from the last section that Aristotle insisted that a heavy object should fall faster than a lighter object. What happened to that theory? You'd be right to say that Galileo put this to the test and proved that all objects fall at the same rate. Well, nearly 400 years later, astronaut David Scott of the Apollo 15 mission to the Moon was able to perform this simple experiment. He dropped a falcon feather and a hammer from a fixed height. What do you think happened? Right, both the hammer and the feather hit the ground at exactly the same time. This is proof that even on the Moon, Galileo was correct. But here's a question for you to think about. How does Newton's law of universal gravitation apply here? Or does it? You might start a discussion group that allows you to review your knowledge of Newton's law of universal gravitation and how it might apply to astronaut David Scott's proof of Galileo's theory. Your discussion group should arrive at the conclusion that acceleration of gravity has nothing to do with a falling object's mass, and that's true whether we're on Earth or on the Moon. In this activity, you'll be tested on your understanding of Newton's laws. Make sure you understand the concepts because they'll help you grasp the more complicated material in later chapters. Ask your classmates to test your knowledge. Okay, let's look at a brief summary to make sure you understand all the points we covered in this lesson. We've learned that Newton's laws of motion are unbreakable, which means that there are no exceptions to these rules. There are 3 laws. The first deals with a body in a state of rest or uniform motion. The second tells us about the object's momentum and applied force. And the third states that to every action, there is an equal and opposite reaction. We also learned about Newton's law of universal gravitation. Now, let's see what the next lesson has in store for us. We've reached the end of another chapter in our exploration of space. We've touched on some important concepts, and now we have a toolbox that we can use to actually do something in space. In our next chapter, we'll find out why we need to think about a spacecraft's orbit and the track it makes over the surface of the Earth. And we'll learn how a spacecraft can change to different orbits in order to get to its final mission orbit.